Okay, welcome to our week 3. Good morning, and thank you for joining me this morning. You can use the chat box just to confirm that you can hear me, and we will start. I hope you can hear me. I always check that. Yes, okay, thank you. Thank you for typing it. Okay, that's me. Let's start week 3. I hope you enjoy your longer weekend. However, we did have a due date last night, but I was checking and almost everybody did good job. Okay, that means week 3, we still in chapter 2, and we have to cover section 2.3, which is differentiation formulas. 2.4, it's the differentiation formulas for trigonometric functions. And 2.5 is a new technique of differentiation, which we will call chain rule. Okay? That means I will cover today 2.3 and 2.4. And I think Dr. Bank will cover 2.5 tomorrow. Okay, that means let's start. What we did so far in 2.1 and 2.2, the beginning of chapter 2, we know what derivative means. That means we did define derivative. We know the definition, the long limit definition. But luckily, what we can do now, we can try to look at some patterns, some connections between the process of getting the derivatives, and we can develop some shortcuts, some formulas. That's probably what you're waiting for, because probably most of you, if you had calculus somewhere in high school or even at college before, you probably remember some of the formulas. That's what I will introduce. Let's see. Let's start with a constant function. Okay. That means we do have a constant function c, okay, just f of x equals to c. And what do you think? What is the derivative of the constant function? Can you type? Can you tell me? Derivative of constant? No, not even. I'm sure you know. Oh, yes, Bradley, yes, 0. Yes, okay, I can see the question mark. But can somebody tell me why is 0? It is 0. Any reason, any justification? Of course, I will be happy with one of them, but let's see. Do you think somebody is definitely 0? The constant function has a derivative 0. But can somebody tell me why? Please do not think about any formulas like as I just mentioned from high school. No. Let's think what we just learned last week. Do you remember how geometrically, having a graph of the function, how we looking at the derivative? Because the slope doesn't change, right? The slope is simply 0. A constant function has it's a horizontal line. Horizontal line has the slope 0, and slope is the derivative. Yes, thank you, Elizabeth. That's what I wanted to hear. We can still use some definition, but we don't have to. That's the limit definition. We can simply say slope, and slope is derivative. That means, please remember, slope of the line is the derivative. Okay, that means this is our first formula. Derivative of the constant is 0. But please remember, just the constant. Okay, just constant function. Not just constant. 1, 2, 3, -1, -3. Just the constant function is 0. Okay. Now, let's try to find, derive the formula. Let's look at the pattern of the power function. Okay, x to the power of n. That's what I have. Actually, before I start, I would like to ask you, if we will have function even x, what do you think? What's the derivative of x? It's 1, and y, it's good, Daniel. Y is 1. Again, please do not think about any formulas, because theoretically we can't even think about the formulas, because I didn't teach you. Because the slope is 1. Yes. Oh, no. We don't really. Okay. Derivative of 0, Bradley, derivative of 0 is 1. No. Derivative of okay, I don't. Okay. I'm a little bit confused. But no, I just like, because the slope is 1. I like the I like one of the comments. The slope is 1. We don't have to even think about any at the moment about any formulas. That means this is line. Oh, it's 0. This is my function x, and slope is 1, which means derivative. Oh, my laptop is derivative is 1. What about the function 2x? What's the derivative of 2x? It's 2. Yes. Now I think that's what I want you to understand. And why is 2? Can somebody try to type it? Because the slope is 2. Yes, slope is 2. That's what I want you to think. Think about always the slope. Slope is the derivative. Great, excellent. What about, I can actually write down, derivative is 2. And we don't have to do anything. What about this one? X over 3. What is the derivative of this? X over 3. Yeah, I did write. It is 1/3, of course, because it's simply 1/3 x. Slope of the line 1/3 x is 1/3. Okay, that's what I want you to know. Thank you, and I'm sure you will remember now. Okay, that's me. Now let's take more advanced functions. But still, this is a linear function. Linear function doesn't change the slope also like the horizontal line, like the constant. That's the reason that the slope is constant, derivative is constant. Okay, but now let's see more complex functions. The other functions, we don't know exactly what is the slope. Okay, that's what I have. I do have function x. We all know that derivative is 1. I'm just using dy dx notation. I think it's okay. Okay, now I do have another function, x squared. This one, the slope is not constant. That means I can't really ask you. But hopefully, do you remember we did in week 2? We went through the limit definition, and do you remember what was the derivative of x squared? It's a new function. Yes, it's the new function which depends on x. It is 2x. Thank you. Okay, now I don't know, maybe we did x cubed also, but maybe somebody knows what's the derivative. It's 3x squared. Okay, and I have another function, x to the power of 4, and I was thinking that maybe we can look at the pattern, what is happening with these exponents. Yes, Bradley, yes, thank you. That's actually my point. Now we can think about the pattern and formulas. If we have x to the power of 1, of course, for the linear function, we don't have to really do the formulas, but let's combine this with the other one. We can see that 1, I can even write x to the power of 0, just to keep the same pattern. The exponent 1, 2, 3 becomes like a coefficient, 1, 2, 3. And the original exponent is decreased by 1. That means if this was 1, now it's 0. For 2, it's 1. For 3, it's 2. That means now derivative for x to the power of 4, it's a new function for x to the power of 3. Okay, and then we can keep working on the derivative of x to the power of n, which will be n, because we can see n can be placed in front, and n minus 1. Okay, that means now this is the derivative of the power function x to the power of n. And I do have this formula. Normally, power function is defined as a x to the power of n, and n is just the positive integer. Yes, like x to the power of 1, 2, 3, 4, 5. But I think your textbook has the proof. Even if n is any, any real number, any actually, okay, we can still use this formula. That means even if x is defined, if n is like x to the power of -1, which is normally not really a power function, because if I will rewrite without the negative exponent, I have 1 over x, and 1 over x is actually a rational function. That's also different. We can look at this formula from different angle, but I can rewrite as a power form x to the power of n to the power of -1, and I can also apply this formula. Please remember. That means let's actually find the derivative. -1 will be placed in front, and from -1 I have to subtract another negative, which -1 and -1 is -2, and rewriting without the negative exponent, I do have -1 over x squared. That's the derivative of the function x to the -1. Okay? That's it. Please remember power rule. We can apply for any exponent and any real number. Okay, that's important formula. We're gonna use a lot. Okay, that's me. Let's try to find the derivative of the function cube root of x squared, and let's find the domain of the function and then later of the derivative. That's me. Let's maybe start with the domain. Cube root, do you think cube root can take any number? Or shall I exclude some? Yes, thank you. Thank you, Joe. That means I can, and actually I even have x squared. That means even if this will be an even root, I can still accept all of the numbers. But in this case, domain, let me switch because I am here, but I will switch the camera because it's covering part of the screen. Okay, that means domain of the function actually are all of the real numbers. I will use this notation. Okay, and now let's try to find the derivative, and then we will look at the domain. That means first of all, I can rewrite this root function as a power in the power form. Okay, again, power function. That means this is x to the power of 2 over 3, because the cube root is telling me what denominator I have to take in my rational exponent. Okay, and now let's just apply the rule. 2/3 will be placed in front, and the exponent, I will take original exponent and subtract 1. And it is not half, it's -1/3. Okay, that's how we applying the rules, the power rule. Always, if you end up having a negative exponent, please remember, rewrite without the negative. Okay? That means negative exponent means that we're placing everything in the denominator, and 1/3 means cube root. Okay? This is really nice form of the derivative. Okay, and now can you tell me what's the domain of this new function of the derivative? Can I accept again all of the numbers? Or maybe I do have one number that I can't accept. What do you think? It is cube root. That means cube root is taking positive and negative. Yes, we have exclude 0. Thank you. That means domain of the derivative are all of the real numbers. However, 0 is. Or if you don't like this fancy notation, you can just say x is not 0. This means all of the real minus the set of one number, which is 0. Okay, all of the numbers, but not 0. Okay, but you can see how we use the formula. Okay, let's keep working on the formulas because we do have a few of them. Okay, now the second rule is a constant multiple. That means that's what I was kind of like stressing out, the constant. Now let's see. We do have a constant c times a function. That means, please remember, in this case, derivative of the constant is not 0. What we can do to simplify, we can put constant completely outside the whole process and just differentiate the function. Okay, just differentiate the function. Derivative of the constant times the function means that we do not differentiating that constant. Constant just stays. And this constant is not changing for 0. It's not 0. Please remember, because the common mistake is to see, oh, you will see constant and you will see 0 times. No, we can't. Like, for example, let's see. Even I can come back to my basic function 2x. We all know what's the derivative of 2x? We don't even have to use the formulas. Of course, 2, because the slope is 2. But if I would like to use the formula, I can say I have 2, constant 2, I can place in front, and derivative of x is 1. That means I did differentiate only the x expression, the variable, the main function. I didn't differentiate constant. That's when you can see constant travels in front. And it's always so easy to put the constant outside and focus on the function. Okay, let's see what I have. I have something like 5x squared over 3. This is quadratic function, no problem. All of the numbers are in the domain. That's me. Now let's see, I can show you 5 over 3 is a constant. Yes, we can see. And the only thing that I have to differentiate is the main function, x squared. Okay, and especially especially fractions like that, because what I will introduce something today, which you probably know, it looks like a quotient, looks like a division. And sometimes we really like to apply additional rule, quotient rule, but we don't have to. Please remember, as soon as x is not in the denominator, it's simply a constant. Okay, and then derivative of x squared is 2x, and now I can multiply back 10x over 3. And my x didn't travel to the denominator, then I can accept all of the numbers. Function, derivative. Domain is also all of the numbers. It's just linear function. Okay. Now we do have a sum and the difference rule. When we end up having a derivative of the sum, it's simply a sum of 2 derivatives. Derivative of the difference is just difference of 2 derivatives of 2 functions. And both of them, of course, are differentiable. Derivative exists. And that's when we can see it's kind of like distribution. I mean, we can focus on one function and then add derivative of the other function or subtract. Okay? And now I do have kind of like all of the rules together, because we just learned the constant multiple rule, the sum and the difference, and the power rule. And don't worry, I can just show you one function, derivative of the polynomial, like addition or subtraction of the power function. Of course, when I'm giving you this, you will probably give me the final answer right away. Okay, don't worry of the middle part. I did like put all of the rules. That means having x to the power of 8, I will differentiate x to the power of 8. Having 12x to the power of 5, you can see what I did. I placed 12 outside and I will focus on x to the power of 5. Negative 4 the same, 10 the same, negative 6 the same, and derivative of constant. Of course, derivative of the constant, 5, we can see is 0. And then derivative of this, my writing is derivative of this, and derivative of x, and then multiply by the constant. That means, don't worry, we don't have to nicely like rewrite everything. If you know the final answer right away, that's the point. Okay, but I just wanted to show you steps. Okay, and then let's maybe use like one of the application, and let's apply all of our rules. Find the points on the curve x to the power of 4 minus 6x squared plus 4 where the tangent line is horizontal line. Okay, that we do have a function. We have to find where exactly on this function tangent line will be horizontal. That means, what do you think? What are the conditions involving derivative for the tangent to be horizontal line? Derivative 0. Yes, excellent. That's what I, really good. Thank you. Thank you. I like the participation. Okay, that means please remember, as soon as you see horizontal tangent, horizontal lines has the slope 0. Tangent is derivative. Of course, the conclusion is derivative must be 0. That means derivative of this function, x to the power of 4, of course, 4x cubed. 6x squared, 12x negative. And derivative of 4 is 0. Okay, that means now we have to solve this third degree polynomial equation. That means you can see theoretically the calculus part is it's done. Yeah, you probably know that calculus is relatively easy. It's just a few rules that we really have to like know them and apply at the right moment. However, to get the final answer, we have to use the algebra skills. Yeah, that's the reason that algebra is so important. Okay, I have 4x cubed minus 12x. I see a common factor for x, and I see x squared minus 3, which could be rewrite as a linear factors, x minus root 3, x plus root 3. And now it's easy. This is giving me 0, this is giving me positive, and this is giving me negative square root of 3. That means that's the solution of our equation. At these x values, tangent will be horizontal. We can also see the original function has only the even powers, which means is an even function. Even function is symmetric with respect to the y-axis. And we can see the symmetry. 0 is 0, of course, but root 3 and negative root 3. What I can do, since the question is asking for the points, we have to take these points and substitute to the original function to get the y values. And I did the math. If we will place 0, we have 4. If we will place square root of 3, we have negative 5, and negative square root of 3 will give me the same answer. And I can show you the graph. Yeah, we can see nice symmetric graph with respect to y. Okay. But the point was, I can still come back, the point was these statements. Because the rest of them is algebra. You should be good with algebra, but that's the calculus part. And of course, the new formulas. Okay, let's keep working. We know lots of formulas. Oh, I have another exercise. Evaluate the limit. Limit as h approaches 0, 1 over quantity 1 plus h to the power of 10 minus 1 over h. That means, what do you think? What I really want from this? This question, I don't know if you realize, because we did this exercise in, I think, section 2.1 or 2.2, when the limit definition was like introduced. Because first of all, do you think this limit looks like familiar? Do you recognize that form? Have you seen before? Something h in the denominator, it's the definition of the derivative, Daniel. Yes, thank you. That means this is definitely derivative of the function at the point A. But we have to identify what is the function and what is the value A. Do you remember we did this exercise? That means now it's a perfect, like to come back to the same type of exercise, because this exercise is combining we testing an understanding of the limit definition and formulas. That means, let's see, first of all, we did realize this, that this limit represents the derivative. What do you think? What is the function that this derivative is defined here? 1 over x, of course, it's 1 over, oh, no, something is missing actually. 1 over x, I'm sorry, I was so excited. Yes, to the power of 10 is the quantity, which of course we always put instead of this quantity. Okay, I have the limit as h goes to 0, f of a plus h minus f of a. And that means this is the derivative at the point a. Okay, that means we can see 1 over a plus h. That means what is the a value? The a value is simply 1. Thank you, 1. Okay, that means we did identify that this limit represents the derivative of the function 1 over x to the power of 10 at 1. That means what I can do, of course, I'm not gonna look at this expression and evaluate like, I don't know, to the power of 10. How can I simplify? Maybe I can simplify in some way, but that's not the point. That means what I will do, I know that I can use the shortcut. Function is defined as a x to the power of negative 10, and I believe I can really fast get the formula for the derivative, which we just learned. Negative 10, x to the power of negative 11. And now, maybe I can rewrite negative 10 x to the power of positive 11 in the denominator. And now I need the same derivative at 1. 1 to the power of 11, of course, is 1. The final answer is negative 10. Let me kind of like, okay, that means this is the work, and this is the final answer, negative 10. Yeah, we kind of did like a circle, identifying the concept, using the shortcuts, and now getting back to the concept. This is derivative at 1, and this is the answer. Yeah, that's we can see that's the way to get this limit. Of course, my instructions are a little bit limited. Maybe I should like type that, oh, please use the definition of the derivative, but I just wanted like you to figure out. Okay, I do have one more like that. Okay, what do you think? Limit as h goes to 0, 1 plus h, the quantity 1 plus h to the power of 100 minus 1 over h. That means again, this is the derivative. Oh, I will use the red color. This is the derivative. And can you tell me at what point? What is the a value? Yes, I think the a value is again 1. This is my a value. But I still have to figure out what is my function. That means this one is a plus h. That means what is the formula of the function? That this, and this is the derivative for this function at 1. It's the quantity, right? X to the power of 100. Thank you. Thank you, Daniel. Thank you, Luna. Okay, and now, who can tell me the derivative of x to the 100? I know that you know, I hope you're typing. Yes, it's simply 100 x to the 99. And if we substitute 1 to the power of any number, it's always 1. It is 100. Yes, Nick, thank you. Thank you for more students being active. That means this is the final answer. And we can see how nicely we can like combine the concept of the derivative and the formulas. I think I do have one more. Let's solve it just in case if you will see this again. Okay. That's what do you think now? It's again the derivative because definition of the derivative is limit as h goes to 0, h, and we have a function minus 3. Would be nice to check if this corresponds, but we can double check. That means this is derivative. And what is the a value for this one? We have 4th root of the quantity, yes, 81 plus h, 81. Thank you, a is 81. And now, another crucial thing, what is actually a function? that we're looking for? The fourth root of x. Excellent. Fourth root of that quantity. That means this theoretically supposed to be f of 81, which is fourth root of 81, and I believe it is 3. That means just checking if it's definitely a derivative. Okay, let's see. You have to help me. This is x to the power of 1/4. That means what's the derivative? Everybody can try to calculate. X to the power of 1/4. Can you tell me? Because I think I was solving too much for you. 1/4, okay, we do have, I am copying from the chat box. Daniel is typed 1/4 x to the power of -3/4. I think, okay, you can confirm if this is correct, but I think this is correct. We can try to rewrite without a negative. That means 1/4. Everything that x value will go to the denominator. 4 in the denominator of the exponent is telling me that is the fourth root of x cubed, or I can put cube outside. Because now I really have to evaluate this at 81. That means let's try. And of course, no calculators, fourth root of 81 cubed. Okay, fourth root of 81. I think we do have the answer, yes, on the top. It's 3. Thank you, Elizabeth. 3. And I still have to cube. Oh, can I manage without the calculator? 3 cubed is 27, Joe, thank you. Oh, and now 4 times 27. 80 plus 28, 108, yes, thank you. Good, yes, good mental calculation. And this is, of course, my final answer, 1/108. Yeah, but we can see the whole process. Of course, again, do not take this and do not evaluate this limit. No, that's not a point. The point is the concept, involve the concept. Okay, I think you're good with the power rules because that's also quite tricky, and the definition. Okay, let's keep moving and learn new rules. What I have? Oh, I have one more question. Let's maybe do it because I don't know if we remember. Probably you do remember. One of the main application of the derivative is derivative as a rate of change, distance over the time, which is the velocity. And then if we will differentiate the velocity again, we will have acceleration. Okay? I hope we remember. That means what the question is asking. The equation of the motion of the particle is given as a third-degree polynomial, where s is measured in centimeters and t is time, seconds. Find the acceleration as a function of time. And what is the acceleration after t seconds? Or I would say exactly at t. Not t seconds, 2 seconds. After 2 seconds. Okay, that means exactly at 2 seconds. That means what we know that derivative of the function is the velocity. I will simply find, okay, I should actually say s. S prime is just the velocity. That means please remember the first derivative represents the rate of change of distance over the time, which is the velocity. And I hope I did correct. 2t cubed is 6t squared, negative 5t squared is 10t, and 3t is 3. 4 is 0. Okay, now what I have to do, I have to differentiate again. That means to get the acceleration, right? We all know that we have to differentiate the velocity, which means with respect to the original function, position function is the second derivative. And I'm not going to ask you, it's too easy. What's the derivative of 6t squared? Of course, this, and 12t and negative t, 10t is negative 10. Okay, that means this is the acceleration as a function of time. And we have to just substitute 2. Can you substitute 2 seconds? what will be the acceleration at 2 seconds? We can substitute 2 instead of t. It's 14, simply because I have the answer that I didn't want to show you. Yes, it's simply 2 instead of time, and it is 14. And since acceleration is the rate of change of the rate of change, that we can see, velocity is just distance over the time. Distance over the time. Yeah, that's the units. And then again, derivative of this function with respect to time. That means we will multiply time, second squared in this case. That means that's the units. Okay. Again, really simple rules, but the concept means the first and the second derivative for the velocity and acceleration, respectively. Okay, that's me now. The next rule. We have to really figure out how can we differentiate a product of 2 functions. We know the sum and the difference, no problem. We can just differentiate and add different derivatives or subtract. But we will probably guess that it's similar, but you know that this will be wrong. And let's see. If I will take a function that is defined as a product of 2 functions, f of x times g of x, and for example, x times x squared, okay? And I will try this weird way, you probably see my question mark, I will differentiate the first function times derivative of the second function. But we can see it still, I don't think it's correct, but let's see. Derivative of x, it's 1. Derivative of x squared is 2x. 2x. Okay? And now, of course, nobody will even nobody even follow this process if you will see a product of the same type of function. That means x times x squared. Fortunately, I can combine. I can get x cubed. And what's the derivative of x cubed? It's definitely not 2x. That means this is actually a correct answer, which conclusion is derivative of the product is not a product of 2 derivatives. Okay? I can even cross this out. Please remember, we can't just differentiate one function times derivative of the other function if the original function was product of them. No, that's not true. Okay? And what I have, I think I have the proof, but I will not really, I can just show you the rules. Okay, that's the rule that we will follow. And I can show you a little bit of proof, but I will not really go through. Your textbook is including a proof. Okay, that's having a function, the product of 2 functions and taking a derivative of it. We will end up following this formula. First of all, I have to differentiate just f and times the second function g. Plus, copy the original function f and times derivative of g of the second one. Okay, that means f prime g, f g prime, addition. And don't worry, I can show you this, but don't worry, you don't have to know, you have to just know the final formula. But I would like to show you that having a product, I apply the limit definition and I did something and I end up with that formula. Okay, that we can see f g prime g f prime. You can switch the order, doesn't matter because it's addition. Okay, that we can see, you can follow, you can pause the video or you can check my slides later, but we don't really have to know how to derive because sometimes students are worried that, no, I just want to show you that none of, like all of the formulas, they really have a reason, they really have a proof. Without this, they will not exist. That's me. Let me come back one more time. That's what we have. This is the slide that we have to remember. Derivative of the product is derivative of the product of f times g means that I have to differentiate f times the original function g plus f times derivative of g. Okay? And we can, yes, read the description. Okay. Product rule, important rule. Okay, let's see. Let me now, how can we, maybe we not really like this one, this proof, but I can just show you based on, like numerically, based on the exact function. If the function is defined as a 6x cubed times 7x to the power of 4, again, this is product of the same type of function. We can definitely combine and avoid the product rule. Okay? That we will probably do this way. 6 times 7, 42. X to the power of 3 times x to the power of 4. It's giving me x to the power of 7. And I'm just using my power rule. 42 times 7, 294, x to the power of 6, done, right? But let's just check. Okay. I will try to use the formula, derivative of the first function times the second, plus the first function times the derivative of the second. That's the derivative. Oh, we don't have to have this anymore. Oh, and we don't have to have this anymore because I did differentiate this. I multiply 18 times 7, 126, 28 times 6, 168, x to the power of 2 and 4, it's 6, 3 and 3 is 6. Adding together, we're getting the same answer. Okay? But of course, we will not, this is correct, but nobody will do this way. Okay? The point is, if I will have a function, let's say like that, I will have a product of x times sine of x. We can see this is product of totally two different type of function, linear function and the trigonometric. I can't combine them together. Then I have to use the product rule. I have to, okay? But I was just showing you that this weird formula for the product works. It's definitely the same answer. But do this way, of course. Okay, let's practice. Okay, that's before, because the next section, which I will cover in few minutes, it's the trigonometric functions. That means at the moment, I can't really use the trigonometric formulas in my exercise because we don't know the trigonometric formulas, but we will learn them in 10 minutes. Okay, let's maybe just practice based on this question. Function h is defined as a square root of x times g of x. And it is known that g at 4 is 8, g prime at 4 is 7. Find h prime at 4. That means, first of all, I have to find h prime, just derivative at x. Okay? That means, let's see, we will use the product rule. Oh, maybe too fast. Derivative of first function times the second. First function times derivative of the second. One more thing, because I put derivative of the square root of x. To get the derivative of the square root of x, we can use, I think we have to use the power rule, because square root of x is x to the power of 1/2, and then derivative will be 1/2 x to the power of 1/2 minus 1, negative half. Rewriting without the exponent, without the negative exponent, we're getting this. And since the square root is quite popular function and it's quite frequent function, I will recommend that you just remember, like, can you see what I did? Derivative of the root x is just 1/2 root x. Okay? You will see how helpful it is. I mean, you can always go through the power rule steps, but it's just as a fun, we can just remember. Okay, that means the second line is my product rule. Now I have to input 4. H prime at 4. Instead of x, 4. Instead of x, 4, 4, 4. And I can, this value is given, and this value is given. Okay, 1/4 times 8, 2 times 7, I think, do you think it's 16? That's 14, because sometimes my typing, because calculating things and typing things are two different skills. Is this correct? I think it's yes. Thank you. Thank you for confirming. 4, this will be 2. 2 plus 14. Very good. That means this is 2. 2 plus 14. Thank you for checking my arithmetic. Okay, but we can see the second line is important for me. Product rule. Okay, now what we will have, we also have to know how to deal with the ratio, the quotient rule. That means the quotient rule is also similar. First of all, please remember, if we have quotient of two functions to differentiate, this is not just the derivative of the top, derivative of the bottom. That's not true. The same way, exactly the same like we proved the product, this will not work. Okay, please remember, and I will erase this. And we do have similar formula, but it will be quotient. Let's look at this one. Derivative of f over g equals to like a quotient, and on the top I have f prime g minus f g prime. In the denominator, I have just original function g, original function from the denominator, but squared. Okay, f prime g, f g prime. That means you probably notice my product rule. Derivative of the product is f prime g plus f g prime. And I know that most of the textbook are switching the order. They putting f g prime, f prime g. But I really like this order because can you see this? If you will get used to that form, then it's exactly the same form for the quotient except the negative. For the addition, I can switch. I can put that term as a second one because adding two numbers, we can use, yes, we can change. We can have commutative property, right? Like 2 plus 3 is the same like 3 plus 2. But when we subtracting, 2 minus 3 is not the same like 3 minus 2. That means you may remember this form and then you will never make the mistake for the quotient. Okay, the same thing. We have to apply this. And I think this is also proven in your textbook. I didn't even type the proof because it's almost identical proof like for the product. Okay. Okay, I have just using words. And let's see my question. Oh, this is not really nice function, but we can see we can't really simplify. And don't worry, you don't have to really like take them. I mean, I don't know if you're even taking the notes, but that's too complicated. But I will apply the quotient rule because we do have a function on the top. We do have a function in the denominator. We always looking for some simplification. But if we can't simplify like this one, we have to just take it like it is and apply the rule. That means derivative of the top function times denominator. Top function times derivative of the denominator and denominator squared. And I did derivative 2x plus 1, copy this function, copy the first function, and just 3x squared. And as we can see, that's the most important line. This is the quotient rule. Oh, and I forgot the square. Oh, okay. And then I did distribute everything and I add the like terms. But that's the last two lines are just the algebra. This is important. Make sure that you will not make mistake, okay, to get this, because that's the quotient rule. And the rest of them is just simplification. Okay, let's see. Oh yeah, for example, function like that. We also see a quotient, but maybe we can avoid a quotient rule. And do you think we can simplify this function before taking the derivative? We do have 3x squared plus 2 root x over x. And since I have only one item, one function in the denominator, then I can divide this and I can divide this. 3x squared over x is just 3x. And 2 root x over x, it's x to the power of 1/2 and x to the power of 1. And I can subtract because it's the division. That means this is 2x to the power of negative half. And now we can see the quotient is gone. Oh, I didn't type my derivative. Okay. Derivative of this is 3. Derivative of this, oh, you have to watch me. Is that correct? 2 and negative half will give me negative 1, and subtracting subtracting 1 from negative half, it's negative 3/2. I can possibly rewrite as a square root of x cubed without the negative. And that's we can see a little bit faster than applying the quotient rule. Okay, that means that's all of the rules. And I do have a summary: constant, power rule, constant multiple, addition, subtraction, and the the product and the quotient rule. Right? That's really important. Oh, I still prefer f prime g, f g prime. Right? Oh, okay, the same thing. Okay, that means that's the formulas that we have to really know them and apply. They are not complicated. Okay, that means the second part of this session is the derivative of the trigonometric function. That means what we expecting to know, another 6 formulas, because we do have 6 trigonometric functions. Okay, that means I can show you how we can get them, and you have to just remember them and apply, of course. That means let's see derivative of the trigonometric functions. That means what we will do, because first of all, we have 6 of them, right? We have sine, cosine, tangent, and then reciprocals, cosecant, secant, cotangent. Let's start looking at the function sine of x, okay, like this one. The graph, because we know that one of the interpretation of the derivative is slope of the tangent. That means looking at the sine function, yeah, we see the blue one. I will try to get the graph of its derivative. That means you can see I did draw a horizontal tangent. Horizontal tangent means slope is 0 or derivative is 0. That means this is 0 because this will be derivative. Again, that's 0, 0. Horizontal, 0, horizontal, 0. And what do you think? What's the slope of this tangent? What do you think? What is the slope of this line? Because I think it's -1. That we do have the value -1. Of course, we kind of like guessing. We still need some tools to get, but yeah, it is -1, and respectively, this slope is. It's +1. Yes, thank you. +1. And again, -1 and positive. That's actually 0. Oh, no, that's +1. Oh, I'm still here. That's +1. Okay, and now if we let's look at one section. Slope, we can see slope is 0, and from 0 is decreasing to -1. That means from 0 is decreasing to -1. And again, from -1, it's actually getting bigger and bigger, and it's getting 0. That means it's going to 0. From 0, it's again getting more steeper, and it's increasing up to 1. But you can see, if I will draw all of the tangent lines, I will plot all of these values. Okay, that means based on the slope of the tangent, we got the values of the derivative. And what do you think? This graph represents what function? Do you think you recognize this trigonometric function? Because this is, of course, cosine. That means this is cosine of x, and I can say, because with respectively to the above, it's the derivative. Okay? That means this is one way to get like approximately get the derivative. Okay, that means this is the first formula. Derivative of the sine function is simply cosine. Sine of x is cosine of x. And I do have the limit definition, but don't worry. In order to get this, we still need some trigonometric identities. Right? And we can see I did start with the definition and I did end up with cosine. Again, you can pause the video, you can double check what I did, but we do have some trigonometric identities that we don't really have to at the moment remember. I just want you to remember that sine of x has derivative cosine of x. Another part. Okay, the first one, 5 more. Okay, now cosine. I have a little bit, do I have, okay, I don't have the, that means this is cosine. And let's try to get the graph of the derivative. That's what I see. I see a constant, I mean horizontal slope, which is, horizontal line has the slope 0. And I need, I see another 0. I see another 0. Another 0. Slope 0, which means the value of the derivative is 0. And 0. Okay, this slope, we know that is -1. This slope of the tangent is 1. And again, -1 and 1. From 0 to -1, from -1 to 0, from 0 to 1, and again. That means, what do you think? What is this trigonometric function? This graph represents which function? Looks like sine, but however, sine is a little bit different. What color I can use different? Sine, actually, sine function looks, oh, my green. It's, yes, it's upside down sine, which means the negative. Sine is this one. Okay, and then we did flip the sign. That means I will remove this sign. We do have negative sine of x. That means derivative of cosine, it's negative sine of x. Okay, good. And I do have the formula. Let me please, we really have to know them. Sine of x is cosine of x. Cosine of x is negative sine of x. Okay, then what we have? We do have tangent function, but we know the tangent function looks, I mean, it's a beautiful function, but based on the tangent, we will not really get the values, because how can I tangent, just one section of tangent, looks like that. Okay, and then of course I can draw it more. And how do I know, like, what is the, like, really steep line, a little bit steeper, and then again, it's not easy. I can tell you, it's not easy to get the graph of the derivative just based on the values of the slope. But what we can do, you probably read this, I know sine and cosine. That means I can use the advantage of it, and I can apply the quotient rule. Okay, that means, let's see. Tangent of x is defined as a sine of x over cosine of x. And quotient rule, f prime g, f g prime. Derivative of sine times cosine, sine derivative of cosine, and cosine of x squared, because that was denominator. Okay. Oh. Okay, I can actually keep my graph. Derivative of sine of x is cosine of x. Derivative of cosine is negative sine. That means, please note, I did change the sign. Negative and negative is positive. Okay, cosine square plus sine square of x over cosine square of x. Can you tell me, what do you see on the top? What identity? What is sine square of x plus cosine square of x? Oh, it is 1. Yes, it is 1. Oh, I am forced to remove my beautiful graph. Okay, 1 over cosine square of x, but 1 over cosine, we know the function is secant of x. secant square of x. That means derivative of tangent is secant square of x. And again, it's worth to remember, rather than applying the quotient rule, we have to know, okay? Because later we will try to reverse them. We will try to do some integration, which is the second part of calculus. That means we really have to recognize the formulas. I don't like asking students to memorize things, because always with the memorizing, I want you to understand, okay? That means we have to memorize, remember, and also be aware of this and apply at the right moment, okay? Tangent of x, secant square of x. Okay, that means what I did cotangent, cosecant, and secant the same way. Okay, that means I don't have to really explain. I will just show you the steps. Cotangent, cosine over sine, quotient rule, differentiation, simplification. I can factor out negative. That's the reason that we're getting -1. And negative cosecant square. That means derivative of cotangent is negative cosecant square of x. Secant, 1 over cosine. Quotient rule, derivative of 1 times denominator minus 1 times derivative of the denominator. And please note, this derivative is 0, because it's just 1, just the constant function. And then we have sine of x, cosine times cosine. And what I did rewrite as a 1 over cosine is secant of x, sine over cosine is tangent of x. That means derivative of secant is secant of x times tangent of x. And the last one, cosecant, 1 over sine. Quotient rule, derivatives, and the same thing, -1. I can possibly write like that. 1 over sine, it's cosecant, cosine of x over sine of x, cotangent, but negative. Derivative of cosecant is negative cosecant, cotangent. And I have the summary? Yes, I do. That means that's the page for you, okay? That's the important page, the slide for you. Please, here, do not make any mistakes. You may probably notice all of the, we have function like cosine, cotangent, cosecant. We call them cofunction, and all of them has derivative with the negative sign. Cosine is negative sine of x. Cosecant, negative cosecant cotangent. Cotangent, negative cosecant square. Yeah, that's what we can see. The rest of them, they could be negative, depends on the value, depends on the points, but they do not include negative sign in the original formula. Okay? That means that's almost everything, but let's maybe solve at least 1 or 2 problems. Okay. X squared times sine of x. That's what we can see. It's typical question to practice the trigonometric and also a product rule, because I really have to apply the product rule now. I can't simplify. 2x times sine of x plus x squared times cosine of x. Okay? That means, can you see I even put the red dot? Do not forget that it is product, because I don't even want to write the common mistake. The common mistake will be 2x times cosine of x, but that's wrong. Product, derivative of the product is not product of 2 derivatives. Okay. Cosine of x over x. Similar things. We can't, of course, we can't simplify, and I can't just differentiate the numerator and denominator. I have to apply the quotient rule. Derivative of cosine of x is negative sine of x times denominator times x minus cosine of x times 1, because 1 is derivative of denominator and denominator squared. Okay, and I think I have one more. Tangent of x plus cosine of x over sine of x. That means this one, I always look at the, if I have only one term in the denominator, an expanded form on the numerator, I will try to simplify. That means I can write tangent over sine of x and cosine of x over sine of x. Okay? I did simplify, I did rewrite, and tangent over sine, if you will simplify this, you will get secant of x. Cosine over sine is cotangent. That means the good thing is I am avoiding a quotient rule. Derivative of secant of x is secant tangent, derivative of cotangent, negative cosecant squared. That we can see how fast we can get this. Let me maybe rewrite. Tangent is sine over cosine, and this is another sine, and that's cotangent. 1 over cosine. This is still not derivative, right? It's just a function. That means 1 over cosine is secant, secant and cotangent. Oh, yes, secant of x cotangent. Okay, that means this is again an example to show you that we can simplify expression before taking the derivative. Okay, that means this will, I think I have more problems, but we can leave it for now. That means this is everything from section 2.3 and 2.4. The only thing actually that is missing is the limits with trigonometric function. That means what I will do, I will put the videos for you, really short, but I don't want to introduce the topic now after 1 hour. I will put the video and please watch that video. It's just a few limits that involves trigonometric functions. Okay, that means I will try to explain, I will solve few problems, and I'm sure you will understand. But please watch the video about the limits with trigonometric functions. Okay, and for today, that's everything. And again, thank you for joining me, and thank you for the excellent participation. I really like that you typing your answers, you answering, and most of the answers are correct. Even if they are not correct, it's an excellent learning process, learning curve. Okay, thank you, and you will hear from me next week. Oh, one more, yes, thank you. One more thing, I think I mentioned this. Always check the module, which is, I think is the last module, practice with Kasia. I'm really trying to solve for you the exam type question, the quiz type questions. Okay, and do not miss any question from these practices. Okay, I will try to solve every week for you the problems. And yes, thank you, Elizabeth. That means please watch them, and you will be more than successful than you. More than you think, more successful than you think. I'm just trying to express myself. That means watch always the practicing with Kasia videos, okay? And this is just the problems, and they are so helpful. Okay, I'm not gonna repeat myself. Thank you, and you will hear from me next week. Thank you.